Welcome back to AI.Code.Cast, everyone. Today we're diving into a problem
Yeah.
that's a real head-scratcher. Coco eating bananas. It's not as straightforward as it sounds.
It's definitely one of those problems that can really trip you up if you don't pay close attention to the details.
Yeah.
But it's also a great example of how a clever technique,
Right.
like binary search, can really save the day.
Okay, so let's set the scene for our listeners.
Yeah.
We've got Coco the monkey, and she's got a serious banana craving. The problem is she's got a whole bunch of piles of bananas to get through, and the guards are coming back in hours.
Right.
Our mission: figure out the minimum speed Coco needs to eat at to devour all those bananas before the guards return.
Right, and to make things interesting, Coco eats at a constant speed. Let's call it K bananas per hour. But there's a catch. She can only eat whole bananas.
Oh.
No fractions allowed.
So if a pile has, say, 7 bananas and Coco's speed is 3 bananas per hour, it'll take her 3 hours to finish that pile, not 2.33. We've got to round up. I
Yeah.
feel like this rounding up business is going to be important.
It's definitely a key detail that often trips people up. But before we get too deep into the solution, let's step back and think about how we'd approach this problem from scratch. What's the most basic way to try and find Coco's minimum eating speed?
Well, I guess we could just try every possible speed, right? Start with Coco eating 1 banana per hour, see if she can finish in time, and if not, bump up the speed by 1 and try again. Keep going until we find a speed that works. It's not very elegant, but it seems like you would get the job done.
That's the brute force approach. And you're right, it would eventually give us the answer. But imagine if there are tons of piles.
Right.
Or one of the piles has a gigantic mountain of bananas.
Yeah.
Checking every single speed from 1 up to the largest pile size could take forever.
Okay, so brute force is out. We need something more efficient. Any hints on how we might find a faster approach?
Well, think about the relationship between Coco's eating speed and the time it takes her to finish all the bananas. What happens to the time if Coco eats faster?
The faster she eats, the less time it takes. Pretty obvious, right?
Right. And that's the key insight here. If Coco can finish all the bananas at a certain speed, she can definitely finish at any speed faster than that. So we don't need to check every speed. We can be smarter about it.
Okay, I'm starting to see where you're going with this.
Yeah.
We know that if a certain speed works, any faster speed will also work. And if a certain speed doesn't work, any slower speed also won't work. It's like we have a sort of ordering to the speeds in terms of whether they lead to success or failure.
Exactly. You've hit on a crucial concept, the monotonic relationship between Coco's eating speed and the time taken.
Yeah.
And when you have a monotonic relationship, a powerful technique comes to mind.
Binary search. Is that what you're thinking?
You got it. Binary search is a super efficient way to find a target value within a sorted range, and we can apply that same logic here.
Okay, but I'm a little confused. We don't have a sorted array of numbers like we usually do with binary search. We have piles of bananas. How can we apply binary search to this problem?
That's a great question. You're right, we're not searching through the piles of bananas themselves. Instead, we're searching through the range of possible speeds. Think of it this way. Our sorted array is actually the range of speeds from 1 banana per hour up to the size of the largest pile.
I see. So even though the piles themselves aren't sorted, we can treat the possible speeds as a sorted range. And that means we can use binary search to efficiently zero in on the minimum speed that works.
Exactly. We'll need to be a bit creative with how we apply binary search in this context.
Right.
But the underlying principle is the same. Keep having our search space until we find what we're looking for.
This is getting really interesting. I'm starting to see how we can bring binary search into the picture, but I'm not quite sure about the details. How do we actually set this up? What are the steps involved in using binary search to find Coco's optimal eating speed?
Well, let's unpack that in the next part. We'll dive into the specifics of how binary search works in this scenario and start sketching out a solution using some pseudocode.
Sounds like a plan. Listeners, stay tuned for part 2, where we'll delve deeper into the world of binary search and see how it can help Coco conquer those bananas.
All right, so we left off with this idea of using binary search to find Coco's minimum eating speed. Have you ever used binary search before? It's a pretty neat trick for finding things quickly.
Yeah, I've come across it a few times. It's like looking for a word in a dictionary. You don't go page by page. You jump to the middle and keep having the search space based on whether your word comes before or after the current page.
Exactly. And that's the power of binary search. It lets us eliminate a huge chunk of possibilities with each step. So how do we apply that to Coco and her bananas?
Well, we talked about how the possible speeds form a sorted range from 1 banana per hour up to the maximum pile size. So I guess our first step would be to define those boundaries.
Right. We need 2 markers, let's call them left and right, Left starts at 1, the slowest possible speed, and right starts at the maximum value in the piles array, which represents the fastest possible speed. Those are the edges of our search space.
Okay, so we've got our starting range. Now we want to repeatedly narrow it down using binary search. How do we do that?
Well, with each iteration, we need to pick a speed to test. And in binary search, we always go for the middle. So we calculate a mid value, which is essentially the average of left and right.
So mid is our current guess for the minimum eating speed. But how do we know if that speed is actually good enough for Coco to finish all the bananas in time?
That's where we need a way to simulate the eating process. Remember, we have the piles array, the time limit h, and now our mid speed. We need to see if Coco can clear all those piles at that speed within the time limit.
Sounds like we need a helper function for that.
You got it. Let's call this function canEatAll. It takes the piles array, the time limit h, and our current speed, which we're calling mid, as input. And it returns a simple yes or no. Can Coco eat all the bananas at this speed or not?
Okay, I'm following so far. We have a canEatAll function that simulates the eating process. So how does binary search use the result from canEatAll to decide what to do next?
That's where the real elegance of binary search shines through. Let's say canEatAll returns true, meaning Coco can finish at the current mid speed. What does that tell us?
Well, if that speed works, then any faster speed will definitely also work, right? We're looking for the minimum speed, so we don't care about those faster speeds anymore.
Exactly. So we can discard the entire upper half of our search range. We update our right boundary to be equal to mid, effectively shrinking our search space in half.
Okay, that makes sense.
Yeah.
And what if canEatAll returns false, meaning the current speed isn't fast enough?
Then we know the minimum speed must be somewhere in the upper half of our range. We update our left boundary to mid plus 1, again cutting our search space in half.
I'm seeing the pattern now. With each step, we're getting rid of half the possibilities, zeroing in on the answers super quickly. So this process continues until our left and right boundaries meet right.
Precisely. And when they meet, we found our target, the minimum eating speed. It's the value that both left and right point to.
Wow, that's really cool. We've outlined the overall binary search logic. We haven't talked about how to actually implement that canEatAll function. It seems like it plays a crucial role in making this whole thing work.
You're absolutely right. That function is where the rubber meets the road. It's what lets us accurately check if a given speed is sufficient. So shall we dive into the details of canEatAll?
Let's do it. Listeners, we're about to peel back the layers of this crucial helper function and get a taste of how it all comes together. Stick with us for part 3. Welcome back to AI.Code.Cast, everyone. We're wrapping up our deep dive into Coco eating bananas, and I'm excited to finally crack this problem wide open. We've talked about the brute force approach, discovered the magic of binary search, and outlined the overall logic. Now it's time to get our hands dirty with the code.
Absolutely. We've got all the pieces of the puzzle now. We just need to assemble them. And the heart of this solution is our helper function, canEatAll.
Right. That's the function that determines whether Coco can finish all the bananas at a given speed within the time limit. So let's break down how it actually works.
Okay, so imagine you are the canEatAll function. You're given 3 things: the piles array, the time limit h, and the speed we want to test, which we're calling mid.
Okay, I'm picturing myself with a list of banana piles, a clock ticking down, and a hungry Coco by my side. What's my first move?
Well, you need to keep track of the total time it takes Coco to eat all the bananas. Let's create a variable called total time and set it to 0 initially.
Makes sense. We're starting the timer at 0, and we'll add to it as Coco munches her way through the piles.
Exactly. Now you need to go through each pile in the piles array and figure out how long it takes Coco to finish it at the given mid speed.
Okay, so for each pile, I'd divide the number of bananas in that pile by Coco's speed. But wait, we have to remember to round up because Coco can't eat fractions of bananas.
Excellent point. That's where we need to use either a ceiling division operation or a bit of math trickery to ensure we're always rounding up to the nearest whole number.
Right, we talked about that earlier. So let's say we've calculated the time for a particular pile. What do we do with it?
You add that time to our total time variable because we're trying to figure out the total time it takes Coco to eat all the bananas.
Got it. So we loop through all the piles, calculate the time for each one, and keep adding to our total time. Is that all there is to it?
Almost. Here's a key optimization. Inside the loop, after we update total time, we check if it has already exceeded our time limit.
Ah, I see. If total time is already greater than h, there's no way Coco can finish in time, even if she speeds up for the remaining piles. We can stop right there.
Precisely. So if total time is greater than h, we return false from the function, meaning the speed isn't fast enough.
And if we make it through the entire loop, without total time exceeding h?
That means Coco can successfully eat all the bananas at the given mid-speed within the time limit, so we return true.
Amazing. Our canEatAll function is a lean, mean banana checking machine. It simulates the eating process, efficiently handles the rounding up issue, and even has an early exit strategy for extra speed. Feel like we've got all the pieces in place now.
We do. We know how to set up our search range with left and right, how to calculate the mid-value, and how to use canEatAll to guide our binary search.
So all that's left is to put it all together into a beautiful, elegant solution.
Exactly. And remember, the beauty of binary search is its simplicity. It's all about repeatedly having that search space until left and right finally converge on the minimum eating speed.
I love how this problem takes a seemingly simple scenario, a monkey eating bananas, and turns it into a fascinating exploration of algorithms and efficiency.
It really highlights the power of thinking critically about the problem and understanding the relationships between different factors. And it shows how a clever technique like binary search can dramatically improve performance.
This has been an awesome deep dive. We've gone from a basic understanding of the problem to a complete binary search solution with all the details and optimizations along the way.
Hopefully, our listeners feel empowered to tackle similar problems with confidence. Remember, the key is to break down the problem into smaller steps, identify patterns and relationships, and choose the right tools for the job.
That's great advice.
And for our listeners who want to see the full pseudocode solution, check out the show notes. We'll have a detailed breakdown there for you to explore.
And if you're feeling adventurous, try applying these concepts to other problems. You'll be surprised how often binary search can come in handy.
Thanks for joining us on AI.Code.Cast. We'll see you next time for another exciting deep dive into the world of algorithms.
Happy coding, everyone!